Hello everyone, just wanted to promote ReproRehab again, all about reproducibility and rehabilitation science. So check it out if you have any interest, and maybe even join if the deadlines are still open. So today what I'm going to be talking about is water quality and how we can get water quality data for a specific zip code that our participants report to us. So interestingly, as I was digging into this, the way that I'm kind of learning about how water quality data is kind of combined and stored within this kind of government backed database is somewhat messy. In fact, probably very messy. So data comes in through the Water Quality Exchange, and it's fed in through not only the EPA but also the USGS and the USDA, and it then goes into the water quality portal, or I guess new data is also fed into this water quality portal as well. And the water quality portal in which the data is housed is basically overseen by the National Water Quality Monitoring Council, and then the data is then available to be queried by us, the users. And since all of these different agencies and are providing data into these overall kind of parent database, it gets very messy, and it can be difficult to really be able to weed through the data that you do get to figure out what you do and don't want. So what I'm showing you today is from a lot of troubleshooting that I have run into, that I think will be helpful to be able to kind of narrow down the kind of path of least resistance to getting perhaps the most water quality data at the highest quality of water quality data that you can then use in your own research. So fortunately, in the water quality portal, although it seems to come in from all these different sources, is kind of organized in a variety of different ways, or in a kind of very complex way, we don't actually have to download any data to our machine. The water quality portal, and I believe it's the United States Geological Survey, has actually created its own R library that can be downloaded and loaded into R. It's called dataRetrieval, and they actually have tutorials and vignettes that demonstrate how to use some of the different functions within this library to be able to perform queries to the databases, to the database, to be able to then get data back. And so it's very helpful. This is actually the first time I've seen this type of documentation that is provided, and this is really only something that's happened very recently. As you can see, this only happened in 2021. So being able to get this data through this type of library is something that is actually quite new, at least new to the date of this video being recorded. And so there is also other documentation in terms of how you can actually use and what kind of parameters you can input into the data retrieval functions that allow us to kind of narrow down our search in terms of what kind of information we want to extract from the water quality portal, and to be able to then merge and associate with our participant zip code data. And so there's obviously a lot of things that you can put in, so it can become quite complicated, but I think I found a way that is a good compromise between what is perhaps somewhat guessing as to whose water quality data belongs to which zip code, and what is actually perhaps the most valid way of doing that in a systematic way. So I'm using the same zip code data that I used before. All I had to begin with was the zip code the participant provided and the state abbreviation that they reside in as well. I padded 0 to any zip codes that have less than 5 digits, and then I used the zip coder library to be able to get the county that the zip code is in, the latitude of the zip code and the longitude of the zip code. And what I mean by latitude and longitude, I'm talking about basically the centroid of that zip code, which is the kind of overall latitude and longitude that reside within the north, east, south, and west bounds of the zip code. So zip codes are not square, but nevertheless they have these boundaries that are generated through census data, that a centroid is kind of derived from those bounds that we then can use as the kind of overall location of that zip code in respect to planet Earth. And then through zip coder I can also get the median household income for that zip code, the median home value within that zip code, and the population density within that zip code. And then of course I can track that for progress. This is the loop that is going to now use the data retrieval function read WQP data to essentially send a query to the water quality portal and retrieve data and return it back to my R workspace that I can then use and manipulate and then store into my zip code data frame. Okay, so the way that this works is that within the read WQP data function, I'm going to provide the latitude and longitude of the zip code, and then I'm going to say it's going to be within some area. And this is where is more kind of art than science in terms of what exactly is the within parameter going to be set to. If it is too large, then you're going to be getting water quality sources from places that perhaps the water quality is not that of which, or is not the water that the person within the zip code is actually consuming. And if it is too small, you're not going to get any water quality data. So this function is not simply going to return what is the closest water quality source to that zip code. You have to define what distance you want to look in to be able to grab that. And through my own kind of trial and error, I found that 80 is essentially a pretty good, pretty reasonable estimation of what we're looking for. But it's probably something that can be improved upon. The reason that I don't use, you can put in what is the state and what is the county, but I found that you are now essentially expanding your search by a little too much. You're being too broad. Obviously there are many zip codes within many counties, and even though you're being more broad, I found that you actually get less data through that method than with this method, where I'm using this latitude and longitude arguments instead of state and county. So when I had first run this through state and county as my input parameters to be able to identify the water quality source, I was only getting half as much data. Half of the zip codes were actually getting data returned to them. When I perform this method, I get probably about a 30 to 40% more. And so that amount of data boost was enough for me to be convinced that even though this is perhaps not optimal in terms of trying to select this parameter, I am getting more data that I could probably be able to have better powered studies anyway to be able to look at my research questions. And so what I'm going to do, so I have latitude and longitude in the area in which I want to find the water quality source, and then I'm going to only be looking at lead. So basically, what is the magnitude of lead measured from these kind of different test times that whichever of these agencies performs, that I can then grab and calculate the mean value of over a course of whatever date I set. So I'm looking at from 2020, because interestingly, some places will only have, even over the course of 2 to 3 years, are only going to have 5 measurements. So some places are going to have much more data than other places. Why this is probably has to do with the infrastructure and the kind of administration possible. to be able to perform these tests fairly regularly. So that is going to vary from zip code to zip code. And so when I run this function, it essentially sends a URL query to the water quality data.us/data URL that then returns my search query as defined within the parameters here, that is then stored in my lead data frame. So one thing that I also learned is that if you're going to loop through, let's say by 1 to the n number of zip codes that I have, even if I'm only going to look at the zip codes that I actually have latitude and longitude data for, and as I have demonstrated in previous videos, even if somebody provides a zip code, they might input it incorrectly, or there just might be a limit, a kind of blank in the data, even if the zip code is legitimate, that you're not going to get a latitude and longitude returned. So even if that is the case, then I plan on just skipping over that, because I don't want to have to deal with this loop crashing because I'm now inputting NAs into my latitude and longitude and getting an error. Even if I do that, interestingly, when I put in a latitude and longitude, and in the case of which my parameter here is probably too small, it will return an error. So this loop would effectively crash, and then I would either have to increase this, which would then have an effect on all the other data that I collect, or I basically have to skip it. And that's what this try-catch method does. It says at least try doing this, which I think is like such a nice way of saying, you know, just give it a go. And if it doesn't work, just keep going anyway, and we'll just kind of skip that portion for the most part, and that result is essentially stored as an NA, which is good, because if we didn't have this try-catch function, which starts from here and ends to here, then we would essentially have to really optimize what would be the parameter of the within area that we would have to use, that we would get at least data for everybody, although some of the data would probably be oversampled from areas that are not specific to some participant zip code. So this would become, I think, more of an issue here. So by constraining this and figuring this out, and this probably can be done a systematic way, then we can figure out, we can get the maximum amount of data without getting too much data that now no longer resembles the water quality data from the zip codes that we're looking at. So when I get that lead data, I then basically remove anything that is an NA value, that is an ND. Some data were reported as ND, and interestingly, some data is recorded in milligrams per liter, although over the majority of measurements are performed in micrograms per liter. So this kind of demonstrates how kind of messy these data can become, and that some tests are reporting values of different units than other tests. And there's no conversion done. They just kind of put in that number, and that's it. And you kind of have to deal with that in the kind of post-processing of this data now. So I'm just looking at lead data that I have a value for, and that is recorded in micrograms per liter. And then I take the mean of that data and I store it within my lead variable in my myzip folder. This code takes a very long time to run if you have several thousand zip codes. Easily this, when I ran this on the nearly 1,400 zip codes I had, it took a little over an hour. So if you have tens of thousands of zip codes, you might want to consider kind of other computing methods that might kind of speed up the process for you. Okay, so I'm going to show you kind of the overall results. So I have 1,397 zip code data. Overall, the number of lead data that is not NA is 1207. So 1207 divided by 1397, I get about 86% of the data are then given a lead value, a mean lead value for that zip code. And interesting, and as I said before, when I just put in state and county here, I was getting only about 600 values that were real within my data set. So I was able to increase it quite a bit by moving to this latitude and longitude method. So then we can look at the data here. We can look at lead. This is log lead. If we want to look at all of these data are going to be heavily skewed, and that's also going to be true for things such as median income. As you can see, not as skewed, but nevertheless, to be able to make it more normal, each of these is going to require some level of transformation. And then now that we have our kind of demographic variables and our lead data, we can now look at some comparisons. And so the first thing that I looked at was, okay, how does the quantity of lead, so the mean quantity of lead in water across this 2-year time span, 2 to 3 year time span, relate to the median income within that zip code. And interestingly, counter to what I thought was going to happen, in that people with lower incomes were going to have higher quality or higher lead concentrations in their water, the reverse appears true based upon these data here. And so in the fact that the higher your median income, the more lead there is in your water. So when I first saw this result, I became very skeptical that everything I had done was incorrect. So I went to the literature to try and figure this out. And interestingly, just within the last couple years, there was an analysis of water quality disparities in the United States in relation to heavy metals and biological contaminants within the journal called Water. And what they had observed was that the one correlation that was significant was that the levels of lead in the water increased as a function of median income. And here this is across states. And so I found this to be at least a bit of a relief, in that they didn't find the opposite result, and I'd have to go directly to the drawing board, back to the drawing board, to figure out what I had done wrong. But this actually demonstrates that this result is congruent to my result and agrees with my result that I had found from the data, that essentially seems to be supported, that the higher the median income, the greater the amount of lead in the water. And so I liked this chart, and so I recreated it here within R. And as you can see, if I were to, that's way too big, then do kind of a side-by-side comparison between this chart and that within that paper, they look fairly similar. Now here, this is parts per billion, and this is, of course, micrograms per liter, so that's important to be able to compare and contrast this. But overall, the median household income is a similar values from low to high. The states, as they line up, are also fairly the same between each graph as well. And so it seems to be supported that, yes, indeed, this is a kind of reproduction of this result from this paper within the data that I was using. And this is, of course, on a small sample when you're considering the overall representation of all 50 states within the country. That, yes, indeed, it does seem to be that, and as they had concluded, that households, where was it here, that that the states with higher average household incomes demonstrate lower levels of copper. That, oh, here we go, with middle average household were still more susceptible to higher levels of lead in drinking water. And so to be able to reproduce that zone is kind of a big crux of what ReproRehab is all about, but also demonstrates that I believe this method is one that can be trustworthy in terms of being able to use it for your own zip code data if you are also interested in how the concentrations of lead in drinking water may impact some outcome variable that you may be interested in rehabilitation. And so I hope you found that this tutorial to be helpful. If you have any questions or want to be able to reach out and grab the code, I'll make sure to try and post it somewhere, or you can always just ask me. And I hope you enjoy this, and I'm looking forward to the next tutorial. Thanks. Bye.